Okay. Some more people are joining us. It's 1 o'clock, so means we can get started. Normally, I will leave some room for people who will be joining us from other classes or something to arrive a bit later. That's fine. But I felt for the first course, at least we should try to start relatively on time because we have quite a lot to go through already in the very first week. So welcome in the course Advanced Analytics in Business / Big Data Platforms and Technologies. In short, we'll just call it Advanced Analytics. That's what we've been calling it over the past years. I will be your lecturer. My name is Seppe, right? And yeah, hopefully we'll be able to do a couple of fun things as every year in this course. You might have heard from other students that the idea of this course is that it's quite hands-on, right? So we will go, and I will explain a bit how that will go. So in this course, kind of how the contents are structured is there is quite a lot of theory, which will be a little bit rapid fire and rapid paced, and that's what you will have on Monday, like today. And then another big part will be those assignments that you will work on in groups, which is, I would say, actually the key part or the main part, even although you might sometimes feel that the theory will go a little bit fast-paced. It's quite okay. Don't worry about that too much. Don't worry too much about the exam. Generally speaking, if you pay attention in the course and you try to stay up to date and you try to do your best together with the rest of your group members on the assignments, you will be able to get the most out of this course. You will be able to make it hands-on, and you will also have no trouble normally to pass as well. So wanted to state that up front, but like I said, I will give a little bit more info. So here you can see an overview of the goals of this course. It's a little bit of a grab bag in the sense that we will kind of go through a lot of different techniques. We'll see supervised, and many of those you will already be quite familiar with, but hopefully we will go through a couple of supervised techniques that you're not familiar with yet, right? Same for unsupervised techniques. We'll also discuss some that you're probably not familiar with yet. Then we will take a deep dive into deep learning. And we will also make kind of the step from working with tabular data to image data there as well. And then from there, we will move on to textual data as well. And there, normally, we will also drag in big data related technologies such as Hadoop. Well, not that much Hadoop anymore nowadays, but we will talk a little bit about it in the sense of giving a bit of history and context. But mainly how you can utilize Spark, because that is something that's still being utilized, how stream processing works, how these other large Apache projects work, how what does it mean to have something in an organization like a Snowflake or a ClickHouse or a Dremio, so from an architectural point of view or a big data point of view, that you can understand those technologies as well. And of course, nowadays we live in an era of generative AI, so it's also important that we discuss that a little bit. I'm even considering to maybe sneak it into one of the assignments. Normally for the text assignment, typically students are working with Spark there, and then they try like a traditional kind of TF, IDF approach or basic text featureization to make a model on top of that. I'm planning perhaps to mix that up this year and to have you play around with like a local LLM instead, because that's more fun. And by now, I mean, those things have become small enough that you can run them on commodity computers basically. So I think there should be something possible there, but we'll see. In any case, the whole idea is that you get solid fundamentals, but mainly pathways so that you can later expand your knowledge further and that you can become a better data scientist, or you can become a good data scientist if you're not a data scientist altogether. So if that's kind of what you would like to do, if you're interested in data and interested in algorithms and AI and things like that, hopefully you will not be too bored in this course. Course goes or lasts from 1 p.m. up until 4 p.m. Unless I get tired, in which case we might stop a little bit sooner, but normally I don't get tired so easily, right? Questions. Whenever you feel comfortable to ask them, basically, that means that you can always, and I will make room, of course, raise your hand during class, but also before class, after class, during the break, you can send me an email, whatever you want. So feel free to ask your questions. I'm pretty available for that, and I try to answer quickly or as quick as I can, even through email. Slides, normally those are available on Toledo a couple of days before each lecture. Likewise, after each lecture, you will also find additional background material there as well. What's that? Typically, the slides or my slides contain a lot of references, a lot of links. Those are gathered and put into that background material section. Very often, I cannot also, or I can't help myself, but to give like an example that pops into my mind and that I discuss in class, and then I also, at least if I can remember to, I also put in the link to that example in that background material as well. Does that mean that you need to memorize everything that's placed under that background material section? Not at all, right? That's just FYI for your information, for if you would be interested, if you would like to know a little bit more about something, you can check that out, right? But that's definitely not something to be memorized. So the slides are basically what contains the main content for you in terms of theory. Sometimes also frequently asked questions will be placed there as well, so you can find all of that on Toledo as well. There is one thing which is a little bit annoying, and that is that we have 4 communities on Toledo, one for advanced analytics and one for big data, and then we have a copy of those as well for students that are following the blended program, meaning they are not here with us physically, but they are here with us in spirit and following along remotely, right? Now, that's very annoying to copy-paste basically all the slides and all the materials across these communities. So if you are in the wrong Toledo community, you will basically see a message saying, hey, you don't need to be here. You need to be in the advanced analytics in business community instead. And normally I've added everybody to have access to that community. If that is not the case, you can register yourself or you can send me an email to be added to that community. If you're like me and you hate the recent redesign of Toledo, right, all the materials are also posted on my website as well, where you can check them out as well. Except for submitting the assignments, that's something that you have to do through Toledo, but you can also find everything in kind of a clean markdown format on my website as well. And that is for students who would be following this course as like a registered PhD student from somewhere else, or just taking the course to kind of audit it or something like that. Or maybe next year you want to kind of follow up on what's discussed, or you want to check a link and you don't have access to Toledo anymore. There are also archives available there as well. So that's another aspect. Let's see. Yeah, course recordings. Those will be made available as well. These are posted typically the evening following the class. So tonight there will be a first course recording. That being said, do try to attend the classes. I have a tendency to write pretty much on the blackboard, and that's also not always visible that well on the recording, and I like to talk to an audience rather than an empty room, obviously, so do try to attend class. But if you can't, or you're sick or something, or you want to re-listen to something, or you can't sleep and you want to use my voice to fall asleep to, those recordings are available for you. In terms of materials, I already said this, mainly what has been taught during the lectures and what's mentioned on the slides, right? So that background material, do not focus too much on, or do not focus at all to memorize that for the exam. So yeah, those are those, yeah, last year it was even worse. We had like 6 Toledo communities. I think now we're back to 4, but you have to be in the one at the top, right? So if your community would be empty, that means that you're in the wrong one. This is our very preliminary schedule for this year's course. Typically, or what you can kind of recognize there is we'll talk a bit about tabular data science, meaning that we'll talk about basic supervised models and then spend a lot of time, or quite some time, on how to evaluate those models and how ensemble models work, mainly tree-based ensemble models. Then we'll make the switch to deep learning, starting with basic artificial neural networks, and then talking about convolutional neural networks and going further to recurrent neural networks later on, and hopefully also talk a little bit about graph neural networks if we have time, and transformer models obviously as well. And then the in-betweens, or basically there is something about tools and platforms there as well. We'll talk a bit about graph databases, but this is all kind of up for making changes, or up for changes depending on how it goes and depending how quick we go through the material. So this is very preliminary, but this is kind of a basic outline. What is not that preliminary, however, is the timing of these release dates of the 4 assignments, right? Those are pretty much fixed in stone, meaning that the first assignment will be available in 2 weeks from now, basically, right? The 24th of February. And the rest of that follows along. We have a bit of an annoying aspect as well, that actually our Easter break lasts for 3 weeks, because we have course on Monday and we have an Easter Monday there. So hopefully we have enough time to go through the material. Otherwise, we'll kind of see what we can do to kind of mitigate that. What do you need? Basic knowledge of statistics helps basic knowledge of very basic analytical techniques, like know what a logistic regression is pretty much helpful. Have basic operating system skills. You're not afraid to open a terminal window or a command line prompt. You have some basic knowledge in terms of programming in Python, right? If you don't be too afraid. Python is a very easy to learn language. If you're an R lover, I used to say that most of the assignments you can do in R as well, but of course for deep learning is not very pleasant. So there I will kind of push you to utilize Python instead. Mainly a motivation, willingness to work, right? That helps as well. And in terms of course, this differs for everybody, right? But the basic idea is that one study point corresponds with 25 hours of work. But that differs depending on how, what kind of person that you are. Obviously, key thing is pay attention to those assignments, pay attention to the course material, try to keep up to date, and then you will be fine. The exam, so that those assignments rather, so those 4 assignments count for half of the evaluation of this course. So 50% is assignments, 50% is a traditional exam with multiple choice questions and a couple of open questions. So what does that mean, that 50% lab report? Well, that's called a lab report because you hand in all of your assignments as a group, right? A group with 5 students. You hand in a report describing all these 4 assignments at once at the end of the semester, right? So in terms of timing, if you get stuck on one of the assignments, you're free to first work on maybe another one that has been released and maybe revisit it later, right? You're free to organize your group as you see fit. If you prefer that one person mainly works on one assignment and then the second person works on the second assignment and so on, be my guest. If you all like to work together jointly as a group on all of the assignments, also okay, right? That's your responsibility, you hand in as a group. Right? I'm not much interested in knowing how you have organized yourselves. I hope that you do that well, right? I'm also not really interested in figuring out or knowing that you guys end up fighting with one another, so try to avoid that, right? If you do end up fighting with one another, let me know as soon as possible so that we can rectify the situation at least, for sure. But you're wise and old enough to make sure that you can handle that basically. Of course, the assignments are released chronologically, meaning that for the last assignment, number 4, you will have the least amount of time to work on that one, right? That's simply unavoidable. Groups of 5 students, what are these assignments? The first one, it follows basically the structure of the course, right? So the first one will be on tabular data, traditional predictive modeling setup, but we will follow like the Kaggle approach. Kaggle is a website where you can compete with other teams to basically build the best predictive model possible, and we'll follow something similarly here. So all the groups will be able to submit their predictions on a given task, and then basically the group that reaches the number 1 outcome gets most of the marks. No, not like that. But basically, we can discuss the approaches of the different groups, and typically, I mean, there has been a lot of debate in the class, like how did this group do so well, and what are we doing wrong, and how can we squeeze out a little bit extra performance out of our model. So that's assignment number 1. And that also means that you will have until the very end of the semester to continue making submissions there as well. Well, not until the very end, because there is one thing with that first assignment that every time, of course, you can basically brute force that system, and you can basically try to continue making submissions until you get a perfect score, right? So half of the data set is made available for you guys to test on, but another half of that data set is hidden and is only revealed up until the very end of the semester, right? And that's kind of to prevent that you utilize these kind of brute force strategies, or you're actually overfitting on the data, even on the test data, which is possible there. Second assignment, there you will switch to image data, and you will apply deep learning approaches. Normally, or to give you an example, in the past years, we had one assignment there that used satellite imagery. Last year, we utilized screenshots that were scraped from Steam. And 2 years ago, it was images of restaurants with kind of the idea to predict which type of cuisine the image was from, right? And we'll see this year if we can find like another fun data set to work with there as well. Then assignment number 3 is on textual data. That used to be text mining with Spark in a streaming setup. Probably this year that will be something with LLMs. We'll see what we can do there, but still in a streamed setup. So maybe combining Spark with like a local LLM and setting that up in some way might be a nice thing to do there, I think. And then finally, we'll have a social network / graph analytics assignment. So there you will work with network data. Sadly, there is oftentimes not enough time left for that last assignment to really build something predictive with a graph neural network, but there is enough time to do something interesting in terms of exploring the data. And there in the previous years, we have been using Twitter data, for instance, Reddit data, we have been using mandates of politicians. We have basically already tried every possible social network that exists, like TikTok, one of the years we did, Instagram, one of the years we did. So I will see which social maybe Blue Sky is a good candidate to utilize this year to see what's going on there. But we still have time to figure that out. If you know of a social network that you really think is cool or would be nice to analyze, of course, let me know. I think that your version of the slides might still contain the date of last year, so obviously it's not Sunday, May the 29th or the 30th, whatever it is, but the deadline for this year is Sunday, June 1st, right? I'm adding in an extra week to give a bit more time for the last assignment there, so normally that should be plenty of time. Also, group formations will go through Toledo, and it will happen also after today's course, basically. So together with the recording later today, you will probably get a link where you can register yourself for a group, right? And again, that's your responsibility. If you already know some people, you can of course register together. You need to make groups of 5 students. If you don't know some people already, just register, don't wait with that, right? Even if you're alone in a group, then someone else can join that group, right? And typically that goes quite well. But do register, right? Make yourself known, don't just not register at all, because then people will assume that you're basically, well, not there, right? And so will I. I will kind of assume that you will not be partaking in the assignments. You have time to do that. I will remind you next week to do so again, right? But then the week following after that, this needs to be done, because then the first assignment will be released, right? So basically you have about 2 weeks to register, which should be plenty, right? So don't forget to do so. If you have a friend group, and you guys have been best friends since the moment you were born, and your friend group turns out to contain 6 people, right? Then fine, we can make exceptions to have groups with 6 people as well, right? Now, try to avoid it, right? If you like one person a little bit less, then still try to do it with 5 people, I would say. But if you all like each other a lot, then send me an email and I will open up one of the groups to contain 6 people instead of 5. If you're the kind of group that want to do it with 4 people, that's also fine, right? But do know that it will be a little bit harder. There are people, especially PhD students, have a tendency to not like others that much, right? So there are people who also prefer to work on the assignments completely alone. I will not recommend it, but again, if that's really what you would like to do, then also send me an email and we'll see, right? Again, that doesn't mean that all of you now suddenly should start doing this alone. As I said, I do not recommend it, but there are options available. But just let me know, basically, right? That's the key thing there. Do you have any questions on anything that I discussed so far, or that was unclear, or that you're wondering about? So the exam is not open book, by the way, so it's a standard written exam, multiple choice open that I mentioned. Anything else? Yeah? Mostly what? What do you mean, Siri? No, actually, neither. So it won't be calculating, that's true. But also not like purely theory in the sense of you need to memorize formulas. The exam mainly tries to poll on your understanding of the things that we discussed. Typical questions are, like a very common question it would be, for instance, something like, explain how an isolation forest works. And why is it an isolation forest? And what makes it different from a random forest, for instance? Example questions? Yeah, well, not a full exam of last year, but I will post some example questions of the years before, so you can get like of an idea what the question style is like. Yeah. Any other remarks, questions, dots? Yeah. No, not really. But if you do want to come by to ask me a question, then send me an email. And the reason is because my main appointment is actually at the University of Ghent. So if you do want to visit me, you can come to Ghent, but I think that that's a bit far. So if you would like to talk with me here, then make an appointment first. Yeah. Other questions? Clear? Okay. Then we can start a hype. First course, you always need to make students a little bit hyped up for what you will talk about the rest of the class. It's always a lie. In the first course, you think, wow, and then the rest of the weeks are theory, but let's have a look. So yeah, setting the scene, right? That is what this is all about. So what is kind of the idea? Well, here you see a little bit of history. We've gone through quite a lot of milestones, if you will. I was kind of thinking that we had kind of seen the end of at least in tabular learning, but even that is not really a given anymore. So things are moving quite fast in the world of machine learning or data science, and today we call it AI, but what's in a name? It's all kind of focused around the same things anyway. Starting from, well, 2011 is an important date there. IBM Watson, which competed in the game Jeopardy and was able to answer like textual questions. Today we laugh at that because ChatGPT does that every day, but at that time this was an enormous milestone. Sadly, or on the part of the team that developed this, IBM then took the name Watson and made it into a whole marketing idea and product marketing kind of approach. Kind of the thing itself went away a little bit. In 2012, we had the release of the AlexNet paper, convolutional neural networks, which, according to many, kickstarted the whole field of deep learning, or at least re-kickstarted the field of deep learning. And then we had Google DeepMing, it should be DeepMind, winning the Go match against Lee Sedol with their reinforcement learning approach, and that became, or ended up in things such as AlphaFold, AlphaStar, AlphaCode, and many others. What else have we seen? This is AlphaCode, for instance, competitive programming, 2022, how young we were back then, right? Image generation with things such as DALL-E, interesting initial results, but also coming from like only a couple of years ago, only being able to generate like very small post-stamp sized pictures. Again, we were sweet summer children back then, right? To, of course, the arrival of ChatGPT and the transformer model that kind of kickstarted this whole new era of generative AI. By no means I need to tell you guys, you probably use that every day. Well, I know that I do. Together with many other models like Claude from Anthropic and Le Chat from Mistral a couple of days ago, and so on. Today we see these techniques being utilized not just for text generation, but we also see AI being utilized for protein folding. We see AI being utilized to discover new materials. The pharmaceutical industry is utilizing this to discover new molecules as well. If you want to, you can check out this website, nextgenmaterialsproject.org, and be surprised by how many new types of materials AI has already, come up with for us. Most of them are not very useful, but from time to time there is like a hit in there, some new idea, some new type of material that turns out to be very useful as well. We have had things such as AI systems surpassing, the level of Olympiad mathematicians. You already saw the claims of some more recent AI systems passing the level of master students, right? So you even have claims of AI systems nowadays surpassing the level of PhD students, right? I already dread the day that I will hear the news that it is also surpassing professors, because, well, then we can just have an AI standing here, which is probably already possible, to be honest. But universities are always a bit slower in the adoption of technology. We see things such as, of course, this generative story continues. Today we have models that are quite capable. They're by no means perfect yet, but they're getting good enough to take one image, right, and generate like a 3D mesh from that, something that I personally like to play with quite often as well. These models have also gotten way better than in the past years. And only you have heard about the dangers from China. So DeepSeek has entered the stage now with R1, a reasoning model, which basically means that it blabbers to itself as it is generating text. Right? OpenAI also has models like these, but they're hiding the reasoning, whereas with DeepSeek you can follow along what they're basically doing, and the model goes, the user wants this, but let me wait a second, maybe I'm overthinking it, maybe I should take a simple approach. And it's basically talking to itself, and it turns out that having these generative models first do a little bit of talking with themselves, that this actually makes them smarter when generating the final output that they can show to the end user. Right? And we used to do that ourselves. That's what we called prompt engineering. We already knew from earlier models that if you put in the prompt, First list your approach or your plan step by step before you give me the final answer. That this already helped, and now basically this is integrated in the model itself. There are a couple of other interesting things that they apply there, which we can talk about later, like GRPO and stuff like that. But basically, the most interesting thing is that contrary to OpenAI, where none of the models are really open, that DeepSeek has also fully open sourced that model. It runs pretty efficiently, meaning that if you have a decently modern machine available, that you can just install Ollama and you can have DeepSeek running on your local machine. And you can integrate that with VS Code, and then when you're coding in Python on one of the assignments, you can just type a command, press tap a couple of times, and the code comes out of that model, right? And already does a pretty good job. So I do not expect the assignments in terms of coding to be that big of a problem for many of you. You can just ask one of these models. Qwen is another model which is actually quite good. And it turns out to be also quite good at coding tasks, which is also why I kind of listed there to give you alternatives for just using OpenAI, basically, which is also a Chinese model here. It's Alibaba that is behind that model. Also pretty good. You can also basically download that locally and have that run locally. So yeah, a lot has changed. But of course, we also have organizations which are not yet busy with the most fancy schmancy AI approaches, but are doing things such as these, right? So if you look at more traditional use cases and perhaps using more traditional data sets, very often tabular data, because data is stored in tabular databases in a lot of organizations, but also a lot of textual data, obviously. But then you run into use cases such as, well, yeah, you want to do fraud detection when you're an insurance company, for instance, right? You have people, I've worked on cases such as these where people deliberately take their car and they crash it against each other, and then the next week they do it again, but then it's the other person that files the claim, and so they try to reutilize the same vehicle to crash over and over again with different insurance providers and basically fraud them like that. You have tax avoidance, you have things such as credit risk modeling, where you try to figure out who will be able to pay back their loan and who will not, or maybe people partially pay back their loan, and then you want to figure out the percentage that they will be able to pay back, right? You want to convince them to buy stuff, right? If you're TikTok and you're building your recommender system, then you're thinking about if the user continues to scroll, what should the next video in the feed be that they are sure to watch. If you're on Amazon, which product should I recommend you, or should I have pop-up over there that you will press buy on, right? So recommender systems are still a big deal in today's world as well. But also obviously where you see kind of similar patterns appearing, that we have moved beyond just using tabular features, and we are also trying to mix in more intricate behavioral patterns in there, maybe even images in there. We are trying to basically embed everything that we can nowadays, and we'll talk about what that means to embed stuff when we talk about deep learning. But also there we see that the data sources that we are using have become much more rich than simply only tabular data. But for many organizations, don't fool yourself. Still today, there are many organizations out there that when they take their steps on the road of machine learning or AI or whatever you want to call it, that for many of them it still starts with very basic business intelligence approaches, making dashboards, making reports, and from there going into more traditional ML on tabular data, and from there maybe expanding further. So for many organizations, there is still a lot of learning involved and a lot of maturity building and capacity and capability building that they need to go through before you can do things like playing with this. And even if you have this running locally, the question then still is, well, what's the purpose, right? Why do you want to use an LLM for? And that is still something nowadays, and that has been the case for many years, that whenever you talk about use cases that involve machine learning and that involve AI, that the purpose of the whole thing, what do you actually want to gain with this, is the most challenging aspect for most organizations in practice and in real life. Theory-wise, you can talk about how all of these things work, but nevertheless, for an organization, for a company, for you, you want to have that bottom line, you want to get some value out of there, right? So, and I know that consultants, they talk a lot about value, 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 but they never bring it. I'm not a consultant. I can tell you that even if you work with consultants, sometimes the value is simply not that clear. You're doing a proof of concept with OpenAI, but you don't really know how much cheaper it would be than just hiring someone, or if it is cheaper, how maintainable it is, or what the development costs are of that thing, or how much the API will cost you every month. So still not that easy in real life, even although it has become to some extent easier. So yeah, these are a little bit the components of data science. I still like to call it data science. I know that it's not the most popular term anymore, but I think it's not a bad name. It has data and science, right? The whole idea there is that we, instead of starting from theorizing or from hypotheses, that we like to start from data that we have, right? Because we believe, we hope that it contains value, that it contains knowledge to some extent. Right? Not all the value and not all the knowledge, obviously not, and it will also contain mistakes and historical issues that we rather would not be having there, right? But that's the whole idea of doing data science, that we start from data and we try to find patterns in there, right? We try to find some sort of knowledge in there. One thing is that by definition, and this is already kind of a blocking factor or is hampering us a little bit, is that we will typically say, and hence the name big data, for most of us, we will say, well, the more data that we have, the better, right? And of course, there are limits to that. There is this kind of curse of dimensionality, and if the data is too old, then it doesn't really matter that you have a lot of it, for instance. But typically, we'll say, well, the more, the merrier. Meaning that for those use cases where you only have very few samples available or very few data elements available that we can use, we will already run into some sort of trouble there. Right? And then maybe you need to go look back to rare event theory or statistical approaches or psychology or something like that to help you a bit more with that. Right? So we do need that data and we do need to have enough of it. Another thing that we will have to admit always is that all the data that we collect is of course historical data. Sometimes we will try to use it to see what will happen in the future, if we make forecasting models and so on, but by definition, everything that we work with is already outdated, right? So there is also something to say, and especially if you move more to a strategic level of thinking, if you want to put it in like operational, tactical, strategical, also something to say to use alternative approaches to problem solving rather than always starting from data. But for us, in data science, that's at least what we like to do. Key issues, what we then need to do with this data is we need to be able to store it, manage it, analyze it. And we will start with the last point there with the analysis of the data. So hence why we will talk about learning algorithms and we'll talk about supervised and unsupervised learning and so on. Not because the two others are not interesting, we'll also talk about those, mainly when we talk about big data platforms and tooling, because those are mainly associated with the storage and the management aspects of the data. Typically, or what you could call this in a bit of a pejorative term, is you could say, well, this is the plumbing, right? You need to make sure that the data gets stored somewhere and that it can flow well. But you can have all of that in like a very nice big data platform, but if you do not know what it is that you aim to get out of the data, right, and how you will analyze it, and then so what? You have your data lake and you're not doing anything with it. Which is also a mistake that many organizations made up until like a couple of years ago, back when big data was an enormous hype. Everybody was building big data platforms because everybody wanted to be like LinkedIn or Facebook or whatever. Yeah, and ended up having enormous data lakes filled with stuff, but no one basically using them or not knowing what to use them for, right? So don't make that mistake. In that case, you can start with smaller data sets and perhaps analyze them in a better way than just first. And this is kind of a negative aspect that especially architects have in organizations. They always want to build the next big platform to replace all the others, and we first will collect all the data that we have, which of course never works, right? After a few years, they get bored or they find some other budgets that they can play with, and then they go build the next platform and they forget about the old one. So that's typically something that fails in an organization. If I sound very negative about all of this, I don't want to be, right? But this is typically what makes this challenging. Terms, don't worry too much about them, whether you call it data mining, big data, data analytics, data science, knowledge discovery from databases, AI, deep learning, decision science. I'm not saying that it's all the same, right? But they do all have the kind of underlying idea of it should come, we should start with the data, and the data can be in different forms, and the models can be in different forms, and so on, and the papers that we publish in might be a little bit different. But at the end, we are concerned about these three questions and about the fact that we want to extract value and knowledge from data. Also means that if you read articles with those Venn diagrams that try to organize these terms in a little bit more of a structured manner, that they will by definition always be wrong. Right? Here is a pretty bad example. Not that I'm dissing the blog, it's not that bad, but this doesn't make any sense. Right? This is completely wrong. So don't go thinking that, if you have data and algorithms, but not features, you're doing data mining. But if you data and features and not algorithms, you're completely wrong, right? I'm not even sure this person knows how a Venn diagram works, but so it's not like this, right? So don't get too confused or don't get too convinced by presentations that would try to attempt something like this. What is important, however, is, well, we want to give them lots of data. We would like to find patterns. We would like to find models. And yeah, instead of hand coding these things, we would like to let the data speak for itself. Typically, what do we want to utilize this for? Very often because we want to predict something. That's our key use case, you could say, or most important use case of the things that we do with data and data science. We want to predict something. You could say, well, forecast something. That's kind of the same thing. Recommend something, that's also making a prediction, right? I'm predicting if you would like this, yes or no. I'm predicting what will happen next week from now in terms of sales that we have. I'm predicting whether this customer will churn, will cancel their contract, yes or no. I'm predicting that if I send you an offer, that you will press buy. And whereas if I do not send you that offer, you will not press buy, because if you also would press buy if I sent you the offer, then why would I send you an offer with an extra discount, for instance, right? So I'm trying to predict something. That those are the key types of models that we try to build in data science. Not always. Sometimes you're just trying to look for certain patterns without having that specific predictive purpose in mind yet, but very often that will be kind of a first step towards making it more predictive. Sometimes it seems that there is nothing very specific that we would like to predict, right? In some cases there is, given attributes of customers, predict me who will leave my shop the next week. There it's very clear what my target is, what my goal is. But let's say you just have a bunch of text that you have scraped from Wikipedia or from the internet. Well, at first, or up until a few years ago, you might think, well, that's just a bunch of text. I can't really make that predictive, right? Well, turns out the whole idea behind training an LLM is to extract a predictive ground task, a very basic general task from all the data that you have, like in text. Such a general task could be, given a partial sentence, well, at least you can predict me what the next token, the next letter, the next word in that sentence will be, right? And that you can do if you just have a bunch of text. And that's called a, we'll come back to that later, but then you move from a supervised to a self-supervised approach. You try to extract the task from the data that you have, and you try to build, and hence why these models are called foundation models. You try to extract a foundational task. Maybe later I'm planning to ask this model to kind of score a review in terms of sentiment. Is this a positive or a negative review? Maybe I'm trying to ask this model to translate English text into Dutch text. Maybe I'm trying to do something else with text, but in any case, I think that it's a good start to have a model that has learned to understand how language works and how text works by having it trained on predicting the next token in a partially completed piece of text. That's foundational enough, and hence why typically these models are called foundation models. And you have similar models for images and video and so on as well, right? For images, for instance, if you would like to have a model that figures out in a quite fundamental way how images work and how the world works, visionary-wise, give it a picture, hide a part of the picture, right, and ask the model to fill in the missing part. Right? I can do that if I have millions of images. That's a simple task that I can come up with, right? For us, if I would take a Post-it and hold it in front of me, right, and I only see part of this room, I would probably be or do a pretty good job to kind of imagine how that missing part should be filled in, right? Well, there are chairs there, so probably the chairs continue. There are people sitting there, so probably there is also a person sitting there, and so on. So again, that's a task that we would like to ask a foundational model in imagery to do. So even well, in the majority of cases, we are trying to predict something. Sometimes we use those predictions to help us decide something, right? To some extent, that's still, for most models, more like a human task. Even if you have a prediction, it doesn't mean that the decision that you should do based on that is always that clear cut, right? Again, with those maybe generative models, it starts to feel more and more that you can also ask something like ChatGPT to help you decide something, right? Or to help make a choice for you. So we are like in a weird AGI zone over there, but let's say for traditional tabular models, again, that's typically a task still up to the human, right? I might give you a prediction that there is a certain customer who is very likely to cancel their contract next week. The decision is still up to you. What do you do with that? Do you then contact them? Do you give them a discount? Or maybe this customer didn't give you a lot of revenue to begin with, so maybe your decision is rather just to let them go, right? So we use these models, but their kind of initial case is to, or task is to predict something, and then we utilize those predictions to help us to make the next step. What else? Yeah, if you talk about predicting also, but we'll come back to that, very often the thing that you want to predict for the models that we build, and this is also a difference from a lot of textbooks that you read or tutorials online, very often the data sets that they will utilize, and when we talk about model evaluation, we'll talk quite a lot about that as well. But yeah, it doesn't make a lot of sense to build a model that predicts something that has already happened, right? Or to build a model that predicts something for which you already basically know the outcome to begin with, right? Because then why build a model in the first place? So very often the thing that we want to predict is something that is still to happen in the future, right? Given my customer base today, I do not want to predict who has already left me, right? That doesn't make any sense. Right? I want to predict who is still to leave me, right? And in a lot of cases, that will be the same. We try to predict things that still will happen. So even if you want to talk about forecasting models, most models in that sense are actually forecasting models. Even if you do classification or regression in many cases as well, you're basically predicting something that is still to be established somewhere in the future, right? There are exceptions to that, but even with the exceptions, in many cases, it's actually more interesting to predict more in the future, right? You could say, like, for instance, house prices. There, you try to, based on the properties of a house, predict the price as it is now, right? Although it might also be interesting to not just predict the price today, but also how the price will evolve in the coming months. That's even a more interesting task. And of course, the more ahead that you try to predict, the more challenging it gets as well. But that's exactly the thing that we try to solve in data science. How do we do so? Well, we use data, algorithm, purpose, and our models need to adhere to these 4 quality criteria, if you will. They need to be valid, useful, unexpected to some extent, and understandable. So data, that's our first ingredient. So the 3 things on the left, you can say that these are our ingredients for a recipe. So we use data, and there I already mentioned it, in whatever form we can get our hands on. So we will mainly in this course look at tabular data, image data, text data, graph data. Right? Those are the types that we will discuss. Very often you will hear people talk about data and using the terms, well, you have structured data and you have unstructured data. And very often what they mean is structured data is tabular data and then everything else is unstructured. I don't like that much, right? Because even text is to some extent structured, right? Language has structure. Let's call that semi-structured then. Okay, but then what is it to be really unstructured? Like just a binary blob of data? Yeah, but you're not really going to use that anyway. So just call the data as it is. Just say you have tabular data, imagery, audio, relational, text, and so on. So this is tabular data. For many of you, you're quite familiar with this already, but just to get like the terminology clear. So we have, this first column is basically just an instance identifier if you need to keep, that's your index in your data frame, if you will, but not something that you will typically use as an attribute in your models, because that's, of course, completely unique, so that's not a good idea. Every row in this thing describes an observation or an example, or as in data science or machine learning, it's typically called, those are your instances. Right? Every column, except for the instance identifier, those are your attributes, or your fields, or your variables, or your predictors, or as you would frequently hear them denoted in machine learning, those are your features, right? And then in this case, there is also like a target column in there, the thing that you want to predict in this case. You have already decided, based on whether it's what the outlook is, and the temperature, and the humidity, and the wind speed, should I play golf on that day, yes or no? And it's already the most horrible example that you can come up with, because if you would build a model on this, it's nice to illustrate how something like a decision tree works, but it's a completely useless model in practice, right? Because, why do I need a model? I can step outside, I can look at the clouds, and I know, as a golfer, whether I should play golf or not, right? Would be more interesting if this column would tell me, should you play golf in a week from now? But again, that's a bit strange, right? To do, that's a decision you can just make before you step out, right? So in fact, it is already kind of not a model as you would see it being utilized in real life cases, right? But something that textbooks like to utilize. So think a little bit about that, this kind of definition of what this target is. In all the data sets that you utilize and find, the target is given to you. But what's important to realize is that there is such an amount of decision making behind the construction of this target variable. Like, why should it be binary, right? Why not multi-class or something like that? Or why not a regression task instead? That this basically influences a lot of the outcomes of your model and also how it will be utilized once it is deployed, right? So also, in the overall process of usage of a model, it's quite important to keep that in mind, right? Another example is, to give the example of an insurance case, predicting potential fraud, again in insurance. Where would you like this model to make a prediction, right? Because this will influence the features that you can actually utilize. If this is the first time a person goes to their insurance agent and they want to file a claim, they do not ask every possible question right at the start, right? There is some investigation that needs to happen first as well, like especially in healthcare insurance and workers' compensation insurance, that's the case. So in the beginning, they just ask a couple of basic questions, like what's the accident or the incident about, some questions about the customer, or some information about the customer they have available, maybe some of the counterparties, but that's already might be difficult to fill in at the beginning. If then your organization says, well, already at that step, I would like to get some indication of whether there might be fraud at play here, then you do know that your model will not be able to use a whole bunch of features there, but only those that you have available at the beginning of that process. Maybe there can be a separate model that also scores the claim later in the process. But this reveals that it's quite important, and that's a mistake that many make, and later we'll see like this process of data science as well. But very often when you read these kind of process diagrams in data science, they will tell you, first step is you prepare your data, you pre-process your data, and then the next step is you train your model, and then you evaluate it, and then you deploy it. Well, the first step should actually be, well, imagine we have the model available already. Let's just pretend it is there, and it is perfect. How would you actually utilize it? When are you planning to utilize it in your process? Who will utilize it? What do you expect to use it for? And that will help you understand much better in terms of which features can I actually utilize and what should my target look like and so on, right? So this is kind of the dry view on a data set, but this already indicates that there is a lot that's going on behind that. Yeah, these features, these can be continuous, right? So numeric, or they can be categorical, meaning discrete or nominal, ordinal, ordered or not. That's the difference between something being ordinal or not. Like a credit rating, right? Countries get credit ratings and they range from AAA to AA to A to B, C, and so on. That's a categorical feature because you have a set of discrete outcomes, but there is an ordering in there, right? Continuous features are not just ordered because 2 follows after 1, but they also have like a magnitude and a scale. 2 is twice as much as 1, right? Be careful because sometimes features, you know this, right, look numerical, like postal codes in Belgium, like Ghent, Leuven, right? It looks numeric, but it's a categorical feature, right? Obviously, because there is no ordering in here. And also, it's not like Ghent is 3 times as high as Leuven is, for instance, right? So these are categoricals as well. We have a hierarchical system in them because the first digit is more meaningful than the last digit. That's true, and that will give some options, but it's still categorical. Yeah, integers as a special case there. If you have non-floating numerical values, like temperature here is just 26, 24. If you know that your feature will only contain like integer values, there are interesting options depending on which model you utilize in terms of converting that to an ordinal representation and making them categorical versus keeping them continuous. But then how do you kind of guarantee that there is never like a floating point that shows up there? So we can come back when we talk about pre-processing, but this is the basic. Target, here it's a binary target because we have yes and no values. So I already mentioned if you have more than a yes-no outcome, and maybe your target is, I would like to predict whether the picture that I have contains either a cat, a dog, or a horse, then you have 3 outcomes, right? Then we talk about a multi-class target, and we do multi-class classification, right? If you already are thinking, yeah, but isn't that the same as just making 3 binary models? Because you can build a separate model to kind of say whether there is a dog in the model, yes or no, a cat in the model, yes or no, or a horse in the model, yes or no. Well, yeah, that's then one of the ways how you could set up a multi-class model or multi-classification task if you only can build binary models, right? Is that always a good choice? We'll talk about that. If there can be multiple targets that appear at the same time, right? So it's not just either a dog, a horse, or a cat, but there can be both a horse and a cat, or maybe there can be none of them. Then typically we say that you have a multi-label model. Not multi-class, but you have a multi-label model. And then from there, you can even go to multi-output models, for instance, where you want to say, well, not only do I want to know which object is in the image, but maybe some of them can appear more than once. Right? So I also want to like to have a count. Like, yes, there is a cat, but the cat appears twice or 3 times, and a dog appears 0 times. So then you can make it more fancy or more complicated. So the most simple representation is just to have a binary target or a single number, and from there you can make them more complicated and make them multi-class, make them multi-outputs, have them predict multiple things. Typically, the more complicated that you make your outputs, the more opportunity you have to do like joint learning and to find correlations between your outputs, because your model might be smart enough to realize that if there is a cat in a picture, it's less likely that there is also a mouse in the picture, but the more complicated it gets, and typically where you will also see people using more and more deep learning oriented approaches, because they make it pretty versatile to also shape the output structure in ways that you want to. Right? Whereas with most traditional tabular models, they will simply say, well, it's binary or multi-class at most, or it's regression, but that's it. Right? So we have instances, we have features, numeric, categorical, we spoke about the target, so that's all good as well. And then our next step or next ingredient is we will use algorithms. And again, here 2 horrible examples of bad ways to organize this. The picture on the left-hand side, yeah, it says you have classical learning, and under that you have unsupervised and unsupervised techniques. That's kind of okay, and some examples of supervised techniques and the 2 main types of supervised, that's okay. But then it says, well, you have a completely different class, which is reinforcement learning, which to some extent, some people do consider a different type than supervised learning. On the other hand, you're also supervising an agent there by giving it rewards. So it's not like it's completely not the same as supervised learning. Why is neural and deep learning in its own category? No idea. Because also with neural networks and deep learning, those are just another technique. You will set up supervised and unsupervised learning systems. So mainly, it makes, and also ensemble methods, these are just a type of methods, those also don't belong in their separate category. So mainly, if you want to organize algorithms, it's better that you talk about types of learning, and which types do you have? Supervised, unsupervised, semi-supervised, you can call that its thing on its own. Reinforcement learning, you can call something on its own if you really want to, sure, right? And those are basically the key types. Right? So the main distinction is actually between supervised and unsupervised. The example on the left actually also shows that not everybody gets this completely right. Like, what type of machine learning algorithm makes predictions when you have a set of input data and you know the possible responses? Of course, they want you to answer supervised learning here, right? Supervisory logic is something that they just made up to confuse you. But what doesn't make sense is that they would say, and deep learning is not this. Now, why not? You can do supervised learning with deep learning techniques, right? So that also this doesn't make any sense. So you have techniques or technique categories on the one hand, and you have types of learning on the other hand, right? And do not mix or cross them in this way. So in terms of learning types, or the 2 important ones, like I said, are unsupervised and supervised machine learning. With unsupervised machine learning, you do not assume the presence of a target variable. You do not assume this column, should I play golf or not? You do not assume, will this customer churn, yes or no? You will not assume, is this fraud, yes or no? Or is there a dog, cat, or horse in this picture? You just have a bunch of instances, basically, with their feature vectors, right? And then the question is, well, you cannot really map an input to an output there. So with unsupervised techniques, the question is more, well, can I find some sort of structure in this data then? Can I find patterns in this data? Examples are clustering, for instance. Can I find groups in this data set? Can I find association rules? If these things are purchased in the same basket, then this also shows up very frequently, right? Very often in unsupervised learning, the way or the thing that these techniques will utilize to find structure and to find patterns will almost always boil down to measures of similarity or distance, if you will, or measures of frequency. the majority of them base themselves on this. Like, what is clustering? You just try to put things together if they are quite similar to one another, right? What is association rule mining? Well, if we see spaghetti a lot in the same basket together with tomato sauce, well, then in a lot of cases also meatballs are in there. Right? So very often they use frequency or similarity as a measure of structure, which is not always what you actually want, right? In some cases, it's more like something being very infrequent or very strange that makes things more interesting for you, right? So then you will enter into kind of an interesting zone of unsupervised learning, which is anomaly detection, which is outlier detection plus, if you will. In typical outlier detection, as we utilize it in pre-processing, we will do that mainly in a univariate way, right? But if you talk about hidden anomalies, right, can be more than univariate, and we'll also talk about some anomaly detection techniques later on. Supervised machine learning, there you do have a target variable, so then it's not as much in terms of what's the type of pattern that I want to find, but basically give me the best function that maps all of these inputs that you have collected, these features, to your output or outputs in some cases. Here we are trying to look for correlations to build a model between our inputs and our outputs, not about causal explanations at all, right? It's simply correlation hunting that we do there, right? Depends on the inputs that you give. Depends on how many instances that you have to begin with. And then the only thing that you can basically change by playing with a different algorithm is the level of complexity that this F can take on, right? Your features stay the same, your output stays the same. So basically, why are there so many algorithms that try to do this? Because they make changes in the way how F is constructed, right? Ranging from quite simple linear models to models that can go very complicated and go very deep, right? So yes, there is also semi-supervised, self-supervised reinforcement learning. We'll talk a little bit about that later on, but these are two main types. So that's algorithms. Yeah, and then supervised learning, you can, of course, cut up further, right, or categorize further. And you have one type which is called classification, where you have a categorical label, and then you have these binary, multi-class, ordinal, multi-label, as I already mentioned. If you have a numerical target that you try to predict, then you talk about regression models or regression learning. What these continuous labels represent, is it a delta or a difference or an absolute value or relative value? You can play with that, you have different options there, but then you're doing regression modeling. I already said that you can have multi-output models as well. In literature, sometimes they will mix up these definitions, right? Some will call multi-label, multi-class, and the other way around. I'm mainly following the terminology that the Python package scikit-learn has adopted, which is what most people are doing nowadays. And in practice, what most people will utilize is binary classification. Even if there would be like a different way to express the task, very often people will try to do that in the form of binary classification. The reason being that it's typically the easiest, and you have the most evaluation metrics available there, and you also have the most techniques available there as well. Is it always the best idea? By no means, but that's what you will see people utilizing a lot. What are other ways how we could distinguish or split up supervised learning? This is the key way how people do it, or the main way. If you read tutorials, they will say, well, you have classification and you have regression. Some will say, well, no, another way to split them up is to say you have discriminative models and you have generative models. Discriminative models, they try to directly model the relationship between your input and your output, your input and your label. They're trying to find the best decision boundary, if you will, that kind of can, in the case of binary classification, that can separate the positive and the negative cases, for instance. Generative models, they say, well, let's take the data and the labels that you have together, and let's try to fit a function that jointly tries to describe both of them. And when you have that, then you also can figure out, well, given an input side, how probable is it that this label then occurs, which is another approach to kind of reach the same thing, but instead of trying to find a boundary that separates your two classes as well as possible, given the data that you have, in the case of generative models, you're trying to find a model that describes the data set as a whole in the best way possible, data and input and output labels together. Less common for tabular learning, but more common in deep learning applications, like generative adversarial models are one such case that we will look at. If we look at autoencoders and variational autoencoders, we will also see how generative models play a role there. Others, and especially in statistics land, they also like to make a distinction between saying, well, you have parametric models, And you have non-parametric models. And the non-parametric models are then very typically called data-driven models. Typically you will then read if you have something like linear regression or a logistic regression, right? That's a parametric model because it has those coefficients in there. It has those betas that needs to be estimated, right? Then using gradient descent or some other optimization technique. What about an artificial neural network? Let's say a small-sized convolutional neural network, where they say, well, this thing has 10 million parameters. Is then that also a parametric model? Is there a point at which you have simply too many betas to still call it parametric? Or if your parametric form becomes complicated enough that it can basically fit any sort of data that you want it to, I guess it's still a parametric model, but I hope that you can kind of understand or agree with me that the distinction becomes a little bit meaningless nowadays. Yeah, if you have 70 million betas, then so what, right? What's the whole point of then describing a functional form? I think mainly the distinction is about, is it you as a modeler that comes up with kind of a functional description that you want the model to adhere to, versus is it more like a decision tree that cuts the data up into pieces, and then the overall kind of decision boundary that you get out of there is then simply something that constructs, or that appears by construction rather than definition, right? But today, don't worry too much about that distinction. And also parametric models are data-driven at the end of the day, because how do you estimate those betas? It's from data. So don't like this that much, but I know that a lot of people will make that distinction. So here's some examples, right? So the idea is that if you have data, that you get a decision tree like on the right-hand side that decides if someone should be refused credit or should be given credit based on constructing this from the data. So not us who go to the blackboard and we try to make a rule set like this, but we try to utilize historical cases to then have a model that pops up out of here. Unsupervised learning, I already mentioned, most of these are frequency-based, distance-based, or similarity-based. Some examples, clustering, anomaly detection. Dimensionality reduction very often gets its own chapter in textbooks, but you could also consider this as being a form of unsupervised learning, right? Because you're learning how to reduce your original feature space into a reduced feature space, right, without using targets. In some cases, you can do dimensionally reduction also if you have targets available, right? UMAP can do so, for instance, but then the basic, if you use something like a PCA, is basically unsupervised, but you're still learning something. You're learning the best compact representation of your original feature space that, yeah, in the case of PCA, that leaves as much variance in there, right? Retains as much long distances as possible. In the case of t-SNE, for instance, retains as much close distances as possible in the reduced feature space. But you are also doing a sort of unsupervised learning there. Most learning is actually about trying to find either representations, and in most cases, compressed representations. If you have something that can do that, even like a compression technique such as gzip can be utilized as a predictor in that case. So here you see some examples, clustering, association rule mining. Hamburgers are frequently bought together with a salty snack and things like that. Very often these association rules, people like to visualize them as a graph, which you can see here on this slide. We'll get back to these examples. Our last ingredient then is our purpose, right? Many will tell you, and again, this is a little bit of something which is easily spoken but not completely true. You could say, well, unsupervised techniques then, because you do not have your targets and you're trying to look for patterns, if you use unsupervised techniques, then you're doing descriptive analytics. And on the other hand, if you use something supervised, like the decision tree that predicts if someone should get a credit or not, or a loan or not, then you're doing predictive analytics because you're predicting something. In many cases, that's true to some extent, but it's not completely true. Because in both cases, the key question again to ask is, what is this model actually built for? What is the purpose of this model, right? And even some unsupervised models can have predictive purposes. And in a lot of cases, predictive models, or supervised models, I should say, do not really have a predictive purpose. Like the example of playing golf, you use the supervised technique to build that, but it's not really a predictive model, right? Because you're predicting something that you already know. To which extent is that predictive? So here you see a couple of different purposes. Sometimes we just want to do something very exploratory. And indeed, there very often we just limit ourselves to basic business intelligence, to making plots, to making reports, dashboards, and so on. We don't make it too complicated. But who's to stop you to use some sort of supervised technique in your exploratory cases as well, right? You're completely free to do that. Descriptive, indeed, unsupervised techniques are commonly utilized here, but it depends a bit on the type of pattern that you want to get, right? You could, again, utilize something supervised here. Otherwise, very often, unsupervised techniques are used for predictive analytics to use them as a pre-processing tool or to use them as a featureization technique, right? First perform a clustering, and then I will use the cluster labels as a feature. Or I will use the distance to the centroids as additional features, right? Something like that. Prescriptive analytics, then, that's about the decision making. You can have a prediction from a model, but that doesn't mean that you already know, okay, but then what should I do? Right? Typically, that is a bit harder, right? A way how to get a little bit closer is with a what-if analysis, right? Let's say your model predicts a certain outcome, and you do not like the outcome. Well, one thing that you could do is ask the model the same instance again, but with some of the feature values changed, and then see if the prediction changes. And maybe over some of the features, you have some control, right? Like maybe we should increase the number of checks that we do for this machine. On other features, you will not have control, right? Like the age of a machine, for instance. So it makes sense that you only play with the features that you have some control over, and that this can guide you in maybe operational changes or tactical changes that you should execute, right? Sometimes using operation research tools to kind of explain or to tell you what you should do to maximize a certain outcome can also be utilized. And maybe a predictive model can be a part in there, right? But perhaps will not give you the complete solution as well. In a lot of use cases, the actual machine learning component is actually only a very small component. There is a lot of stuff around that happens as well. But that's our purpose. So I already told you it's a good idea to think backwards. In every use case that you will find yourself in later, when you talk with business stakeholders and they want you to utilize whether it is ML or AI or DeepSeek or ChatGPT, a good question to always ask is, well, assume that we have the model already. Assume that we purchased the API of OpenAI, or assume that our model is trained and we validated it and we get a perfect accuracy. It works well or well enough. How will this be used? What will you do with the predictions? Which features will you be able to give that model at the time of usage? And try to think from the production backwards to the pre-processing. Because if you know that you will not be able to utilize certain features, it doesn't make sense to already include them in your development cycle to begin with. And that's something that happens a lot. In organizations, first results of a model are not spectacularly good, and then people start coming to you. And I have this data set here, and maybe if you include that in your model, it will do a better job. Sure, I can try that. But let's say that it does a better job. Where did you get this data from? And will you guarantee that then, when this model is put into production, that you will be able to continue to deliver me that data in a timely manner? Is this something you just found somewhere under a table one time? Well, yeah, I can test it out, but then it's not really a predictive model anymore, right? But because to be predictive, the model will have to be used in production. It's not just a one-off that we're doing here. So purpose is key. And also, most use cases in business, they're not really about machine learning if you understand them a bit better, but they're more about automation, which is fine, right? But that doesn't mean that you always need ML to do automation. Sometimes simple heuristics can also solve that. I'm not the first one who says that. This is also, I mean, a lot of, even at Google, their first rule of machine learning is don't be afraid to launch a product without machine learning. They themselves say, well, very often you can rely on basic heuristics. And in any case, that's a good idea. Also, if you would be building like a forecasting model, and you built your very fancy LSTM and whatever, and you're pretty pleased with the results, always at least benchmark it with a very simple heuristic. What if we just take the same sales value that we had at the same date, but last year? How good is that model? That's the most simple model that you can come up with, right? So always have like some heuristics, some benchmarks in place that you can test against. Others found that very, or maybe not so surprising, you can spend weeks optimizing accuracy or area under the ROC curve or MSE in a model, but at some point, this will not translate in business value of that model anymore, because maybe they become harder to maintain or harder to deploy, and what's also the case is that very often the metrics that we utilize to quantify predictive performance of a model are already some kind of proxy value and some weak representation of all the benefits and costs that happen in the real world that we are not fully capable to incorporate in this evaluation metric that we're using. Right? So also there, be a bit careful in the way how you set up these models. Okay, key criteria, and then we'll stop for a quick break. Valid, useful, unexpected, understandable. So what do these mean? Well, valid means, and this is actually the key one, especially for predictive models. If it's just a one-off, maybe they don't need to be generalizable, but for predictive models, our key concern is we want them to be generalizable. And what that means is our model should not simply work well on the data that we've utilized to train it on. It should also continue to give us good predictions when we confront it with new examples going forward. Right? Where these new examples come from, sometimes you have quite stringent requirements there, right? Sometimes you know them beforehand. You might say, well, I've built this model for Germany, but I would like to test it out for the customers in France as well. If that doesn't work, then you either know that you need two models, or you might want to think about a single model that encompasses both countries, but something that could be tested. The one thing that's annoying for us, because we can't really control for that, like with the France and Germany example, we could at least say, but if we know that our model is not capable to handle new countries, we will simply not have it ask or deal with those new countries. We can build a separate model for that. The only thing that's hard for us to control is, of course, the arrow of time. And there we're a bit stuck. Because on the one hand, the whole thing that we want to use our predictive model for is to make predictions. And is to make predictions on instances that will arrive tomorrow, next week, next month. And the whole thing that I've utilized to train that model to do so is already historical data. The future will not be exactly the same as the past. So I do know for sure that at some point in time, the reality that my model is predicting on has drastically or has significantly changed from the reality that it saw back when I trained it. Right? That's fine, can't avoid that. But this is exactly why we will split our data in a train and a test set, and where typically the test data instances come at a later point in time than the train instances. Because already there, I would like to get an estimate, some idea of the volatility that's present in my situation that might cause my model to still do a good job for the cases of 2022, but already break down in 2023. And even if that would be nice, or my model would do a good job, I also have the burden to continue to monitor my model as it is being utilized, because it's not back when I trained it that 2022 and 2023 were okay, but maybe now we are 2030, right? And a nuclear war has broken out, or maybe a new COVID or whatever, right? And the reality has changed again. So also in production, I should continue to monitor my models and still see whether they generalize well. If they don't, what do you do? Well, typically the answer there is, well, we should retrain them from time to time. When we talk about model evaluation, I will come back to that point of retraining, and I will rant a little bit about that, but certainly that's a solution. But the key thing is, of course, that as a developer of a model, that you kind of have an idea of how volatile is this whole thing and how long will this model stay fresh for. We try to set them up in such a way that they do a good job for as long as possible, but in all of the models that we built, for the vast majority of them at least, I should say, the enormously vast majority, we kind of feed them data when we train them, but then we stop teaching them, they stop learning, and they are in kind of a mindset that is exactly the same as back when we trained them. And even for fancy models like something like a ChatGPT, there is a reason why they continuously retrain these models, and why they say I have a knowledge cutoff up until this point, right? And the interesting thing is that at least you can kind of push these models based on the prompt that you ask to kind of pretend to know, today is this date, and so probably today this has happened, right? And they give an impression that they're doing a good job in terms of updating themselves, but they really are not. Their parameters are fixed, right? Another way how you can kind of cheat your way is you can pretend that they have memory by from time to time taking something from your previous conversation that you had with ChatGPT and sticking that back into the prompt and going, well, look, this is what you spoke about previously. Please try to take that into account. But the model itself, those 60 billion parameters, or how many they are, probably even more in the case of ChatGPT, the latest models, these stay fixed, right? You have approaches that play around with having the weights of a model also continuously update as it is making inference, as it is making predictions. But those are in practice still very rarely utilized. Not because people are afraid that you will get runaway models that kill all humans, right? Please don't believe those kind of pundits. But because it's simply too intractable still to do that. And they don't work that well yet. It's easier to just retrain them from time to time or to fine tune them further from time to time. So I hate when people in media or in newspapers say, well, the big power of machine learning and AI is that these models are self-learning. Yeah, what they mean is they are self-learning during training based on the data that you feed them. It's even worse when they say, and because they are self-learning, they can continuously learn from their mistakes and become better and better. No way, they don't, right? A random forest that you train once and makes a lot of mistakes will not magically get better by itself over time, right? It will get better if you keep track of those mistakes and you retrain that model, sure, but not on itself, right? That's still a human inference or interference, at least, that needs, or intervention, rather, that needs to happen there, right? So that's why generalization is so important, because even although ChatGPT could hallucinate about something that happens next year, it will not really know unless we retrain it, right? So models will decay over time, sadly, but that's what happens. And we would like to keep them as useful as possible for as long as possible. Why? Because this helps us, and of course, the more stable a model is, the more safe it feels, and we can avoid like breakdowns and maintenance costs and so on. A model should also be actionable, meaning that, yeah, a lot of models can give you predictions, but how do you use that prediction, right? I already gave the example of churn modeling, where you want to predict that a customer is going to leave you, yes or no. I once worked on such a case for youngsters, so the young customer segment for a financial institution, so for a bank here in Belgium. The model itself was not doing a bad job, but of course what's not so easy is if you do know that someone has a high likelihood to leave you soon, what do you do, right? Their idea was, well, let's have one of the agents in the branches randomly call those people and just ask, are you doing okay? Is there something we can do? But it makes for a weird conversation, right? Because in some cases you get the answer, well, you can't really tell them, hey, we believe you might be thinking about leaving us, right? Sometimes they will tell you, in which case, okay, fine, you're thinking, is there something that we can do? But it's not easy to make that very actionable. In other cases, that is very easy. In other, like in telco, you can send them a discount automatically or something like that, so there it's way easier. Another aspect there for models being useful is if they're so costly to maintain, it might also not be a wise decision to keep them around, right? So useful also means they should be cheap enough, or at least not prohibitively expensive, right? Which still for a lot of LLMs today is kind of a challenge, that they're quite expensive also in inference. They should be non-obvious. A model that predicts you things that you already perfectly know, you will not really use that model because you are your own best model in that case, right? So should be unexpected in some way, should be non-obvious in some way, should involve maybe some weird data from time to time as well. And then depends also, this is not like a very strict one, but at least you hope that for humans, the models are also understandable. We would also like to learn something, right? Now, that depends. There are use cases where people will say, well, for us using a black box model, an understandable model is fine, right? But typically we'll see that people, and especially for stakeholders to get trust in the model, they will ask questions such as, why is your model wrong in this case? Why did your model predict yes instead of no in this case? Why is your model less certain? What would make it change its mind? So people will ask a lot of questions, even if your model is black box, that you need to be able to give answers for. So we'll also have a little bit of a chat on model explainability later on as well. So there's a couple of other examples. Yeah, valid generalizable. The most famous story to talk about here is the tanks story, which no one is really sure whether this really happened. It's more like a little story that became more and more exaggerated over time. But the basic idea is that when artificial neural networks arrived, the US Navy was planning to experiment in using such a model to detect camouflaged tanks of the enemy. So what they did is they set out on a field trip and they took lots of pictures, like the one you see on the left-hand side, of the field with a tank in it, and then also pictures, of course, with the same fields without a tank in it. And they labeled them, yes, has a tank, no, this picture does not have a tank. They fed it through their neural network, not as many parameters as we would have today in a convolutional neural network, but okay, good enough, did a good job. So they were quite pleased. They went to their generals and they said, General, we have a model that can detect camouflage tanks quite well. Fantastic. Generals are smarter than scientists, so what the general will say is not, I believe you, but they will say, like, let's test it out. And so they planned a couple of weeks later to go out with that model, a camera attached to it, take a picture, no tank in the field. What does the model say? Oh, tank. And then there was a tank, and the model says no tank. So it was basically completely predicting at random, right, all over the place. Scientists went back to their drawing board, took a closer look at the pictures they had taken, at the weights of the model, couldn't really figure it out what was going wrong, right? Except that, of course, when they hung all the pictures on a whiteboard and then they took the same pictures that the general had taken on the day when they tested it out, and they hung the pictures next to those, and then, of course, they immediately saw what was wrong. And the thing that was wrong or was different between the two sets of pictures was the weather. The model had not learned to detect whether there was a tank or no tank. It simply had turned out that when the scientists had taken all of their pictures with tanks in them, the weather was still clear. And by the end of the day, when they were taking the pictures with no tanks in them, the weather had become overcast. So what they had built is basically a model that learned whether the weather was cloudy or not. And then, of course, when you test it out on a different day, the model goes completely crazy. Today, we would have an easy time to spot that using some model explainability techniques that we have that can open up that black box a bit, but that's how the story goes. Like, be careful, because these models will try to use the simplest correlations, of course, to link with your outputs, not the ones that you actually want to. Like I said, whether this really happened or not, you can read the mentioned link that tries to figure out where this story actually came from. A lot of textbooks will sell this story as if it really happened, right? I'm the one telling you that we are not so sure, but it is still a good example, right? There are things that did happen. However, at some point, Udacity was trying to teach an RL agent how to drive or how to control a car. Luckily, they didn't use a real-life car. It was a virtual representation in like GTA or some game. And for reinforcement learning, you need to give a reward function. And they said, well, you know, let's keep it simple. We will reward you based on keeping a certain constant speed over time. Because if you do that, that means that you must be driving. Typically, if you crash, your speed goes down, right? What did the car learn? Well, I'm going to spin in circles, because that's how I can keep a constant speed, and the easiest thing for me to learn, in fact. So there are a lot of kind of things where we see that models, they tend to do a good job based on the data that we give them, but then if you try to utilize them on unseen cases in the real world, they break down, and that's what it means for a model to be generalizable. So in ML, what we try to do is we try to hunt for generalizable correlations. If you want to put it in a nutshell, that's basically what we're doing. Not causation, not claiming that, but at least we want generalizable correlations, right? So it's a little bit better than just finding a correlation that only worked once. Right? You have a website called Spurious Correlations, where every day they post like a graph between two things that are heavily correlated, right? Those are things that might have been correlated in the past, sure, but at least we want to make it generalizable. That's why this idea of using a test set is so crucial in machine learning. And in fact, you could say so it makes it different as a field than statistics, because we use statistical models in ML as well. But typically what a statistician might not talk about, at least at first, is they will say, well, I have 20 observations. I will come up with a model that I believe is as simple as possible, so parametric, let's say linear, right? I will fit that model, and then I will talk about the goodness of fit, right? Using R-squared or whatever measure that you want. And a machine learner will always tell you, but the challenge is not to find a model that has a good fit on your training data, because with the models that we have, we can fit any sort of training data perfectly. The challenge is to find a model that continues to work well, also in instances that you did not give it, right, and can generalize. And that's of course, it's not like these two fields hate each other on the term, of course, they align, but that's kind of the key difference between, if you ask, statistics versus ML. A typical machine learner will talk or will tell you that it's about generalization. Actionable, some examples here. At some point, Netflix, a long time ago, wrote out a $1 million prize. And the whole idea was, well, we have a recommendation system, obviously, at Netflix. But if you can make our recommender system a little bit better, you win $1 million. And indeed, a lot of people around the world started working on that data set that they published. And indeed, there was a team that was able to beat Netflix and do a better job than them. They got rewarded the money. But Netflix took a look at the system that they had set up. And what the engineers at Netflix said was basically, well, this system is so convoluted, so difficult to keep running, so difficult to maintain, that we'll actually not adopt it. The 1% or 2% in additional performance that we get is not worth it, right? So it's not useful in practice. What can be useful? Well, if you want to make a model to reverse engineer a rule-based system, also not really. Let's say that, and this is also sometimes a problem in real life with supervised learning. In fraud, you see this a lot. And typically there, the whole idea is, okay, you enter an organization, like an insurance company or a credit provider company, and they say, well, we want to use machine learning to detect fraudulent cases. Okay, do you have historical examples? Yes, we do, because we already have some rules in place that flag potential issues, and then a human will look at them closely and decide whether it's fraudulent or not. And we have a couple of those cases from the past, right? Problem number one, typically companies keep around the cases that a human checked and were denoted as being fraudulent in the end. But do you also have the cases that were flagged but denoted in the end as being non-fraudulent, and the cases that were not flagged and not looked at to begin with? No, we only have the true positive ones that went all the way. The rest you should all consider as simply being negative. Okay, one issue, but fine. You build a supervised model on that. Might even do a pretty good job. Right. What have you built then? You have basically a supervised model that has replicated the flags that were already in place to flag those cases. And maybe is fine-tuning that a bit to then see, okay, in this group, which ones are really fraudulent and which ones are not. But you still have replicated that flagging-based system, because what was not done is, of course, the investigators, they don't have a lot of time, so they never randomly pick cases that are not flagged to check them. Right. So then, and this is what will happen, the organization comes back to you and they present the results. You're very proud because your AUC will say, I have 88%, that's actually a good model. Your organization goes to the investigators who hate you because, of course, they think that you're building an AI model to replace their job, right? So they already hate you from the moment you step in. And they say, but your model is rubbish, because all the cases that it found, we would have checked anyway. Right? Or system that we have in place already would have flagged those already anyway. So what new stuff is your model actually doing? Answer, nothing. Of course not. Right? Of course it's not doing anything new. You could have just kept that system that you have. You don't need a model. So then, but we would actually have hoped that your model would give us some new types of strange behavior, of fraudulent behavior that we currently don't know about and we don't have time to look at, and the system is not flagging. Yeah, but if you label those guys as being negative anyway, what do you expect that the supervised model will pick up on that? Right? So then typically that's a point also where you first need to switch to anomaly detection, find the most anomalous cases, and sit together with people to figure out, well, are these really fraudulent, yes or no, and then maybe go to a supervised model or have something that works in tandem there. So also goes to show that you can supervise model everything you want, but in most cases people care more about novelty than relearning the past, right? So keep that in mind as well. Unexpected, these are things such as, if you type with proper capitalization, indicates some degree of creditworthiness. Which web browser you utilize indicates if you would be a better employee or not, especially in the tech field, right? If you're still using Internet Explorer 6, maybe that's saying something about you. At some point, insurance companies were trying to utilize your style of posting on Facebook to kind of indicate if you're a better driver or a worse driver. That luckily never really got implemented. Facebook was not so happy by that. And yes, sometimes if you do route planning for UPS drivers, it can turn out that it's not the shortest route that is the best one, but the one that optimizes for making right turns, because it turns out that that's quicker than finding the shortest route where you have to make more left turns because you end up waiting for other cars more often. Of course, not everything which is unexpected is also interesting. And then interpretability, I already mentioned it there. You can have a black box model, but people will ask you questions such as which features were now the most important? And if age goes up, does the target go up? Or is it the other way around? Or why did your model predict fraud in this case? Or why did your model predict this in this case, right? And very often the answer is more and more, well, it's a black box model. We can't explain it. Just trust the model. But of course, people won't do that, and rightly so, right? So we also need to look at some explainability techniques, or maybe use an explainable model to begin with, if we can, to also help us a little bit as end users of these models. And then as a fifth one, more and more you could also kind of question, yeah, and should models be fair? Should models be ethical? Some examples about, yeah, sexist models, racist models. There have been books written about this as well. Also nowadays, we know what people are doing with LLMs to spread propaganda or misinformation. There is this whole AI slop theory and that internet theory, and you've noticed it yourself, that every news website that you open nowadays, or recipe website, that it's already filled to the brim with this kind of AI bullshit, right? Not even mentioning what people are doing with deep fakes and fake video and so on. Of course, that's a question that we will have to solve, and some people are trying to solve and so on at some point. Companies like Anthropic are working on ways to prevent models or LLMs from being jailbroken, but that remains a challenge as well. So, of course, there is also kind of this ethical aspect that's at play here. And of course, Europe there is trying to do their best with the AI Act and stuff like that. It would be nice if they would also try to do their best a little bit in terms of technical innovation, but so far they have only done their best in legislative innovation. But it is important as well, right? Just to mention that. Okay, I suggest that we go for a break here. Let's take a 15-minute break and then continue with the rest of the slides. Okay. So I already spoke a little bit about the process aspect behind it. This is a quite old picture, but it's one of the available approaches that tries to describe the process of analytics or of data mining or data science, if you will, a bit. Very often they are quite alike to one another in the sense that very often they will start with some understanding of the business problem as a first step, then selecting your data sources, cleaning your data, typically transforming it in different ways, all of which can be considered to be like the pre-processing phase and where typically 80% of your time is being put in. The actual analytics running the model is quite fast, especially if you do not take too large of a set of possible algorithms that you want to try, and very often there is also no need to do that to begin with. And then the interpretation and the deployment is kind of all put in this post-processing phase over there. This is a very similar one. This is called CRISP-DM. This is, we could say, the most popular one. Stands for Cross-Industry Standard Process for Data Mining. At some point, they were planning to make a second version, which never really happened. If you look at processes for AI and generative AI, they actually look quite similar than this one. Bit better in the sense that at least this shows that there is like a cyclical aspect at play here, that deployment, maybe over time you would have to revisit that model and that business case. And it also shows that, of course, sometimes you need to take a step backwards, whereas this maybe just tells you that you go from left to right and you never have to stop or go backwards, which is obviously not the case in real life. There are some others as well, like SAS had SEMA for a while, and there is the drivetrain approach, which is not that bad either, but generally speaking, these models kind of lead you through the same steps there. So obviously, this is what a real process looks like. It's not uncommon that you need to take, like I said, a step back. In some cases, all the way back to the identification of your business problem that maybe you understood not well enough, or you want to revisit the way how you codify your target, for instance. So this is also the reason why many of these machine learning projects are quite hard to manage, and to some extent even harder than it is for typical software engineering projects in terms of time management and budget expectations and so on, is because it's very rare that you can kind of quantify at the start of a new machine learning project, especially if it's the first time that you're using a particular piece of data or you're working in a particular kind of context, to kind of make an estimate of, one, how long it will take for this project to finish, but also two, what the performance will be at the end of it, right? Which makes managing the set of this pretty challenging. So whether to apply like waterfall, well, that definitely not. That's not really going to work. A lot of people see agile and Scrum-based approaches as kind of a good way to manage data scientists, which to some extent there are good aspects in there, but it also quickly can lead to certain aspects of mismanagement. One particular thing about Scrum is that you have like your daily stand-up and your backlog that gets filled there, but also that doesn't align always that well with data science, because sometimes the model is just training and you're waiting around, and sometimes something doesn't work and you need to start from scratch again. At some point, maybe it also is worth asking the question, well, if this is something that started as an experiment and we see that after a couple of months we didn't get out of it what we would have hoped to get out of it in terms of predictive performance, maybe switch to some other idea rather than trying to keep that alive and losing trust again and losing stakeholder trust in that whole project. This leads, or so the kind of the danger there is that you can kind of end up with data science model factories, where there is not a lot of creativity in terms of what your data scientists can work on, and very often this happens in organizations where they have centralized the data science team somewhat, and then they try to find projects to work on in the rest of the organization. And especially if the rest of the organization doesn't really have a good clue of what ML is or what AI is, they will very often end up giving or asking for use cases that are actually quite similar. And very often boil down to, tell us who the most valuable customers are. right? And you build up, or you end up implementing 50 different versions and 50 different models, but that all kind of answer that same question. And I've often kind of made the joke, but half seriously, like in some organizations, if you would take all the models that they have built over the past year, and all of them score their customer base, and you would take all of those scores that they output on the customers and look at how correlated that these scores are with one another, probably you would have 50 different models that all end up giving more or less the same probabilities or the same predictions at the end of the day. So not really a good idea to do it that way, because in that sense, or in that case, of course, your projects will not be very disruptive, will not be very innovative, and you can also in many cases not expect that people from other departments in an organization will give truly like disruptive use cases or use cases that are maybe endangering to their own position as well. So it's not easy to manage these things and to utilize ML in a way which really can bring value to the table at the end of the day. So here you can see some other things that can go wrong. So what this quote highlights is there is a misalignment very often of the technical and the business expectations. The outcomes are consumed by business teams, of course, but when they start without a clear alignment between business and data science teams, then you end up in kind of a failure state where models will not be accepted. The data scientists will look at AUC or accuracy, and of course the business team will look at financial benefit, we'll look at costs, we'll look at business insight, and so on. Also, the article makes the case against, well, data science should not be managed as just a group of people that execute and are just building models. Basically, what you hope to get out of all of this is to develop profound new business capabilities, but of course, that's way more easier said than done. If you're a very engineering-driven company, like if you're like a Spotify or a Netflix or an Uber, then maybe in those cases, that's a little bit easier to do. But like in a traditional organization, I mean, it's very hard to set up your data science projects and teams in a way that this can really happen. So same for deployment of machine learning, like I already mentioned, and keeping this thing running. Also, that is something that's quite hard for a lot of organizations, because again, it's a little bit alike, but also not completely the same as traditional software projects, where you have continuous development and continuous integration, or you have test-driven development. With machine learning models, you can do some of these things, but we also know that they tend to decay and fail silently over time as reality changes. So the aspect of ML ops took quite a while for enough theory to be settled around that, the operationalization of machine learning models, and what do you do with them once you have deployed them? How do you monitor them effectively? How often should you maintain them? How often should you retrain them? Of course, nowadays you have the same books, but with the title AI Ops, and there it's about very similar questions. Let's say you plan to use a language model. How do you maintain it? When do you retrain it? Do you have to fine-tune it, or is it better to just buy one from one of these big players? How do you set up guardrails? Should you use an LLM judge to use as a judge for the output of another model? Is that a good approach? Is that not a good approach anymore? Will that change tomorrow? So these questions of, well, we know that the technology is there and it's all nice and handy, but in practice, there are still so many open questions in the sense of how do I now effectively use these things that were unanswered for quite a lot of time, or luckily now we are beginning to figure out the answers for. Same for the data scientist as a person. Obviously there has been like a lot of claims that if you want to make like a high salary, you should become a data scientist, and it's incredibly hard to find a person like this, because maybe we expect these guys to be both good at business management and developing, and they should be creative, and they should have a PhD and be good researchers, but of course you will never find a person that contains all of these skills in one person. Luckily, already organizations have also realized that this is not a single person that you're looking for, but this is a team that you're looking for. And where maybe some people are better at the knowledge transfer or the requirements elicitation between the business side of things and the technical side of things. Maybe some people are very good at doing the development part or the research part. Maybe some people are good at presenting or visualizing the results and so on. What you see in terms of role placement, but again, this has changed a bit, but like, and I do not fully agree with this, but like what a lot of organizations and companies and things like DataCamp, the way how they say as well, you have basically two main types of people. You have a data engineer and you have a data scientist. And those are two separate roles, right? Two different roles. Although it's not exactly clear if you look at most of these infographics, like in which sense then that they're really different from one another, right? Because they all do kind of the same. They both should have business understanding. They both should have data understanding. But it seems like the engineer, they mainly do like the data importing and cleaning, and then the scientist, that's the one that you need to do the actual statistical modeling and machine learning. Poor data engineer, right? Because basically what you have created is like a little data slave, right? Or a janitor, I will say. Like, you clean all the data for me, right? But you don't build the models, right? That's for the data scientist to do. Whereas the real job description of the data scientist is just to import XGBoost and press run on the XGBoost model, right? So in that sense, you're not doing like a lot of science there, and neither should you. XGBoost is fine for most use cases anyway, right? And only very rarely will you have to come up with your own loss function that by some magical means will be better than the ones that you already have available in that library. So it's a bit associated to like the junior and the senior role of data science, if you will. But I'm not always sure that this is the best approach, because the best way to make someone very unhappy in an organization as a data scientist, I mean, imagine if you would go apply and they would tell you, but the first 2 years you can't actually work on any models, you can only clean data. You leave, right? Well, unless the salary is enormous, but still then you would be very depressed. Likewise here, they also come up with, well, you do not just have a machine learning engineer, but you also have a data engineer, and those are separate, and then you have a data analyst. But again, here, if you look at the different bubbles and the colors, they all seem to be more or less the same. The only thing that I can kind of gather from here is that a data scientist basically still needs to be able to do everything, right? So it doesn't make a lot of sense. And yeah, of course, people need roles, because the more roles that you have, the more budget that you get, and then you can tell your manager, yeah, we already have a data scientist, but we also need a data engineer. So next year I want to make my team bigger, but also don't think that it is anything less than that, right? It's just marketing, and you do have different roles, but it's more about then what's the actual content of what you do. And today you will have prompt engineers that people hire, right? And LLM experts, so you can also add them to that group as well. Maybe it's better to say, okay, what you actually need is, and what you typically see is you have people that you do need business experts, right? You do need to understand the business problem, and no way you as an outsider that you will understand all the intricacies of what's going on in the business case that you're working on. You will need people that are like warehouse engineers, data warehouse engineers, or database administrators, but typically you already have those in your organization. Legal experts, also not to be underappreciated, especially in today's age of GDPRs and AI acts and so on, or just working with personal data, asking for consent. What can we use? What can't we use? It's good that a couple of lawyers first checks that before you go implementing your model. Business enablers, people that can do the conversation between the business end users at the end of the day, the people that will actually end up using the models and listening to their requirements and expectations and so on. So this is a multidisciplinary team, not just a single unicorn that you're looking for. Likewise, for big data, also there is a reason why so many of these projects have failed, or if people or organizations talk about big data, why they like to talk about them, but in not a lot of cases did these things succeed. If we then move more to we move away from the analytics side and we move more a little bit to the platform or big data stack side of things. What has happened there is that there are a couple of challenges across these things. Like, people or organizations think that they have a lot of data, but they never think about the quality of their data, or the amount of noise that they have in their data, or even where to find the data. For many organizations can already be a challenge, right? So it's about data management as a whole, not just, let's build a data lake and then all of our issues are solved. Organizational aspects, politics in organizations plays more of a role than you would hope for in a lot of cases. For analytics, maybe not having labeled data, because the most interesting cases to predict are exactly the cases that you have never predicted something for historically. So then how do you train a model? Other failure modes, or people do not understand how much effort there can be required in pre-processing. So there are a lot of things still that make this hard in practice and that make this challenging in practice. And mainly also the aftercare. So the interpretation of the models by your experts. What are trivial patterns? What are unexpected patterns? Doing sensitivity analyses, deploying your models into your business setting, and then definitely the monitoring and the backtesting of models, which all of these things were, in a lot of cases, the forgotten part of data science. If you look back at the models that I just showed, like here, it's basically called, well, you have this post-processing step here, and then you're done, right? And if you look at CRISP-DM, it's like, deployment. But there is a lot that happens there, right? There is a lot that needs to happen there. And very often it can be as simple as, oh, well, the code that the data scientist made is a bunch of Jupyter notebooks, but not exactly the most maintainable bunch of code that we ever saw, right? It's more like a stack of spaghetti that no one wants to touch. So also there requires like careful governance of, it's fine that you experiment and your code is a bit messy, but once you want to put the model into production, there are certain higher guarantees that you want to ask there, right? So this is such a challenge in organizations that we even wrote a book about this, me and my colleague, about managing the different types of risk in terms of models and how they can fail. We should update it for the ChatGPT age. It's on the to-do list, but it's busy enough, but hopefully we can get there sometime. So yeah, these big data stacks, so the 4 or the 5 or the 6 or the 7, you can find different versions, but the 4 V's in this case of big data, you have the volumes, the velocity, the speed, right? The veracity, the different types, and the variety, the different types, and the veracity, the quality levels of the data. Of course, also makes it challenging, but we're going to start with the analytics. Later, we'll talk more about big data and the different platforms there, because you do not need to have huge volumes of data or high-speed data to do interesting analytics, right? And the other way around, it's not because you have large volumes of data that the analytics come for free. And that's certainly something that we will revisit, because if you look at these Hadoop-style platforms or Spark-style platforms or Flink-style platforms or something like Apache Druid or newer things, they all concern themselves with, let's store the data and let's have pipelines of data where you can send events to one another. But okay, still then, how do we become smarter with that? How do we get some insights then out of all of this data? How do we build analytical models? That doesn't come automatically, right? So that's still a separate concern to question or to wonder about. So a bit of separate worlds there. I mean, if you have big data, you need a way to deal with it, but it's not because you have a data lake or a data warehouse that, tada, your analytics side of things is done, right? Not at all. And indeed, it is about technology, and we will talk about technology, but like I said, we'll have to be a little bit critical there. Enterprise IT is also often slower than the rest of the world or the open source world and things that are happening there, meaning that whereas today in the open source world, especially if you look at the Apache Foundation, they have maybe concluded that Hadoop was maybe not the best choice, and even Spark was maybe not the best choice, and we will do more things with Polars, and we will do something with this. That once you go work in an IT team or in an organization, that there's still very often a couple of generations behind in terms of technology adoption, which is also a reality that sometimes you will have to live with, right? And you have to deal with that. You can't always like use the latest and greatest that's out there. So yeah, we'll talk about HDFS, but what's also important is like these technology choices. These are difficult challenges for especially like an IT team of a small-sized organization. Yeah, should I use BigSQL, Hive, or Slurv, or should we buy something like Cloudera Hortonworks, or should we go to Snowflake, or should we use this? And we have just bought Spark, and now you tell me that there is this other new thing that I should be utilizing instead. This is what makes kind of IT in the enterprise pretty challenging, as we will see once we talk about big data. But we are going to start with the analytics first. So later we'll come back to this. Okay, I have a little bit of time left. I will not use the full time, but I will do at least the introduction of what we will talk about next week. And what we will do next week is, for many of you, this is not really new. So we'll get through this relatively quickly, but hopefully there will be a couple of interesting tricks in there as well. So we will start with our, let's say, tour across this process, starting with tabular data for now, and starting with the very first step, which is pre-processing. And more interestingly, also typically there, the step where you perform some feature engineering, right? Trying to come up with interesting features out of the ones that you have already. So this is, for now, remember, where we want to go towards. And I've replaced here at least the play golf example with, will this customer churn in a month from now, yes or no, right? So still a binary classification, but a more predictive-oriented question. And again, I have a unique index, which I will not use as a feature, obviously, but I do have their age, account activity, and so on. Why? Well, because most techniques assume that this, if you work on tabular data, that this is what your table has to look like. They have the requirement that you stick everything into a single table where basically you have a list of feature vectors. Right? Every instance is described by a vector of features and has a target associated with it as well. It's typically not where you start from in a lot of cases, right? Because you will start from a collection of data sources spread out all across the organization. And even if you would have a nice single database, even that nice single database will typically have a lot of normalized tables in them, where now we're basically asking you, well, you should denormalize them and stick everything into one single huge spreadsheet again. So you will have to aggregate or de-aggregate in certain cases, and probably you will also have things such as, let's say, missing values in there that you will also have to treat, and outliers and so on. So it takes a lot of time before you have something that's kind of ready for use for your analytics. And hence, that's why constructing such a data set takes work. You need to merge. Maybe you have information or you have certain features that work on an individual level, but you want to predict something on a household level. Well, then you need to come up with ways how to aggregate the individual to the household. Or the other way around, maybe you know something about the household, but you want to predict on the level of the individual. Well, then maybe you can copy those features, or you can think about de-aggregating them in certain ways. And so on. How you define your target, right? We have spoken about this. Probably there are multiple ways to define your target. Again, if you take the example of this, what does it mean that you're a churner, right? Why a month from now? Why not in 2 months from now? Well, that depends on what you plan to do, right? If you're a financial institution, well, if you're a telco, I will give a couple of examples. If you're like a Proximus in Belgium or a Telenet, churn for them typically really is the customer uses their easy switch number and they leave you, right? It's a very clear decision for a customer there to churn. If you ever switched banks in your life, right, you probably did not really close all of your accounts completely with the bank that you were at first, unless you were very unhappy for some reason. But typically what customers do there is they move all of their money out. They change the account number for which the salary should be paid to, but they leave like a couple of bucks on the old account because you still have the bank card, and maybe, who knows, it can be handy someday, and it doesn't cost you too much. In some cases, it's even free to have a checkings account open, so you never really close that. Then if you would say, well, churn means that you really cancel all of your accounts, you will not have any churners, or barely have any churners, right? Or only really the cases that were super unhappy with you. So there you would have to say, well, churn means that if this is our timeline and this is your account balance, that you say, well, you're a churner if for at some point your account balance was below a certain threshold. Yeah, but that won't work, because if you make big purchases or you lose your job for some time, well, of course it will be below the threshold, but you will not really be a churner, right? So maybe it needs to be below that threshold for a sufficiently long period of time. Yeah, but you have people who are just poor, right? So maybe before that period of time, there should be a previous period of time where on average it was above this level of threshold, followed by a drop. So you need to monitor people for long enough in order to be able to say, well, for this guy, you're a churner, right? So then you could say, well, if you work historically, right, well, at which point in time will you assign the label churn to this person, right? So I can say I extract your features at this point in time, and then I observe you for a while longer to see whether you're a churner or not, right? But I need to observe you then for at least, let's say, 2 months to be able to tell that you're a label 1 or that you're a label 0, right? So this also indicates like how far ahead can I predict. I know that I should keep you around for 2 months, and only after that moment I can really determine that you were a churner or not. So already just the question of how do you put a yes or a no in this column, there is a lot that happens behind that to kind of indicate that. Same if you talk about like predictive maintenance for a machine. Yeah, you can predict that a machine has already failed, but that's not very interesting. So also there, typically you want to predict that a machine will fail in the future, right? So this takes work. Your data set needs to be large enough, obviously, but not so large that your model training takes ages. Typically, things that but you know this obviously, but of course, including instances that are too old, is it still very useful to have house prices to predict on if the last transaction or if the transaction date of that price was 50 years ago? Probably less so, right? Or maybe you can use an index to re-index those prices and to bring them more to levels of today's monetary value. That's the way how you could resolve that, but typically speaking, you want to have instances that are as close to the today as possible rather than far away. Definitely also something that you can't do is include information that in your features that you would not have available at the time of making a prediction on your instances, right? So everything that you stick in your feature columns is part of your feature snapshot and is something that you should have available at the time of running your model, at the time of inference. You can't look in the future there. To construct your targets, there you can look in the future, right? Because that's what you deliver in training, and that's what you not have when you run your model, right? So your target is typically something that will happen, right? But to get your picture of your instance, your snapshot, that's at a fixed point, right? And can't use anything that will happen in the future. You might say, well, duh, of course, right? That makes sense. But also sometimes this is easy to miss. You wouldn't believe it, but there indeed exists systems in real life where they have a mix of, they have a table where they have like a customer ID, 11111, and timestamps. And they keep like a full track record of fields that were changed over time, which is nice. If you see this, you're already very happy because that means, I can not only see what this customer looked like at this date, but I can go back in time and also see what they look like at this point in time, right? So I can basically have their full trajectory. I do not just see their latest states today, but I can also go back in time. Except, and we've had this happen, except there is one field in there, one column, and whenever there is an update to this column, it also backfills and overrides all the previous updates that happened in that column. Guess which feature turned out to be the most predictive one? If you look at the feature overview in terms of importance for that model, this one, right? Yeah, once you know it, you can kick it out. But if you would never check it, and no one would ever tell you, it's just a feature like all the others, you don't really know. Hard to spot these things. So in any case, your finished model will not be able to look into the future. So there you will, if you do cheat, you will basically see that you did something wrong there. This also means that in terms of data splitting, I will talk about cross-validation and so on, but at least for your test set, first of all, I would always recommend you to have a test set. Second of all, have that from a different period in time than your train set. So do a temporal split, not just a random split, but a temporal split. And do that split as soon as possible. Not after your pre-processing, before your pre-processing. And I will tell you why later, right? But as soon as possible. And you keep that test set stuck, hidden. You don't look at it for as much as you can. Right? Of course, you will look at it at some point, and you will look at it multiple times, and you will cheat. It's unavoidable, but the idea is at least that we don't look at it until we're really ready to perform our final evaluation of our model. So yeah, then the idea is you can use different data types, not just internal data, but also external data can obviously be helpful to make models better if you talk about feature engineering. Yeah, things like scraping social media, or using weather data, or even using Google Trends is what people have done, web scrape data and so on, open data. There is a lot of data obviously out there that you can utilize. This is an example of where people have utilized Google Trends to help in real estate prediction. This is an example where Street View has been utilized to kind of predict. I think the left-hand side is predicting the likelihood that the house will be involved into a car accident because it's close to the street and it's easy for a car to hit it. And the right-hand side is basically utilizing Google Street View to predict the state of a house, whether it was recently renovated or not. This is research that we did in the department here as well. So there are interesting data types, point cloud data and geospatial statistics also that you could utilize and so on. Different types, already mentioned this a little bit as well. Yeah, metadata can also be useful, which is typically data that describes other data elements, but for a predictive use case can be helpful. For instance, again, if you talk about fraud detection in an insurance claim, you have the things that people write on that claim itself, but also just the when was this claim last updated. It's not really something that's on the claim, but it says something about the claim. Or how many times did it get an update in the past month? So these are exogenous elements of data that describe your main data elements, but can also be quite interesting to include in a predictive model as well. So then typically your next step, once you are gathering your data, obviously you do a bit of exploration. What I will mention here is this debate on this topic. Very often, this is what people also call EDA, or exploratory data analysis. You will have some people say that it's a bad idea to do this. And you will have some people say, well, you should avoid doing any sort of exploratory data analysis and making these kind of plots and correlation plots and so on. And the reason why people will mention that typically is they will say, because what you might do by doing this is you might be adding bias to your process. The things that you kind of see at first sight during kind of an exploratory analysis is going to impact your mindset in terms of what will you expect your model to pick up or what you will expect your model to do. There is something to say for that. In any case, it is true that if you hunt a little bit and you do some exploration, there will be things that maybe pop up to you and that your model does not pick up. And you will think, strange, why did this happen? Or there will be things that you expect your model to pick up, and indeed your model does pick up and might make you believe that your model is doing a better job than it's actually doing. So certainly there is some truth in there. On the other hand, if you talk about bias, there is another aspect of bias which is more important than maybe you, by doing your exploration, maybe biasing yourself a little bit. And the other aspect of bias is, of course, the data that you're using, since it's historical data, will, by nature, by definition, it's made by humans, will already contain a lot of bias. And the whole goal is, in terms of doing this kind of exploratory analyses, is maybe not to add more bias ourselves, but it's maybe to at least be aware of some potential issues of bias that might already be present in the data. Right? So that should be a little bit your mindset when you kind of are exploring your data, is to see what might be potential issues at play there. There are tools that make this easy. Things like Pandas profiling or AutoVis or SweetVis don't make all of these plots manually by yourself, or ask DeepSeek to make plots for you right nowadays. Most important ones here, well, yeah, of course, histograms, box plots, they are interesting. A correlation plot, still a good idea, because correlations can still mess up a lot of things that you use down the line. Also for more complicated models, not that they have issues if you have like correlated variables in there, but sometimes then if you use explanatory techniques, it might be important to be aware of correlations in your data. Another reason, like I said, that this idea of bias is nothing can tell you a better story than a visual. This is the famous example of these 4 data sets that have the same mean of x, mean of y, the same variances, the same correlation between x and y. And if you make a linear regression model, you get the same model for all 4 scatter plots. So, but they look obviously widely different if you visually inspect them. So hence the idea that doing some exploration is not such a bad idea, right? Next step, also easy enough, is cleaning. Typically you check for consistency, making sure that your categoricals are coded in the same way, or the different representations are being brought to the same common format. Again, doing that check that you do not have future features or future variables in there, or that got modified according to the target at hand. The one thing that you sadly, so typically people say, well, there are 3 big issues, well, except for noise and duplicates and stuff like that, but like for a modeling technique, 3 things that can screw them over. Correlations, which indeed is typically the case for statistical models or for explanatory techniques that you use on top of more complicated models, but indeed important. But if you use a particular type of model, you could kind of ignore it. Outliers as a second type, which again for many statistical, more simpler models, annoying, but maybe if you use certain other types of models, you could also ignore them. But there is one thing that you can basically almost never safely ignore, and those are missing values. Even although you have techniques that in theory can deal with them out of the box, and you don't need to do anything special, very often the implementation that you're using will nevertheless ask you to fix them still. Right? So very often the kind of blocking pre-processing step, even if you would ignore everything else, still a technique might complain about the fact that you have missing values in there. So most techniques cannot deal with these. What does it mean to be missing? Well, there can be two reasons, right? So very often people will say, well, a variable has missing values at random or not at random, right? And at random basically means, well, it was unknown or it was non-disclosed, right? Like in the case for age, right? We might have some people for which we do not know the age. Doesn't mean it's not applicable, simply because we do know that every person has an age, right? So there is no discussion there. So the reason why it's missing there must mean that they never told us, or we never asked, or we don't know it. If you have a missing value for a credit card limit, well, that's perhaps less at random, right? That might be, well, if you do not have a credit card, then you simply, it does not apply to have a credit card spending limit, which is different than the value 0, right? 0 would mean that you have a credit card, but we put your spending limit on 0 because you were spending way too much on Temu, right? So detection at least is easy. You can open your data set in Excel and you can see that there are missing values. Well, I say that, but if you have a large table, for instance, that's my style of humor, right? If you have a large table, it might still be difficult to spot your missing values in practice. And another thing that might make it difficult is maybe for one column, missing means that there is an NA in there, and maybe for another column, it's 0 that means missing, or maybe -1, or maybe an empty string, right? So if you have a mix of garbage data like this, even already the detection cannot be as simple as you think, right? So you will need to keep your eyes open a little bit and to do like defensive coding there to kind of figure that out. Now, once you do know which values represent missing ones, you have a couple of treatment options at play there. Delete is kind of the nuclear option, not really recommended. For instances, you could, right? But even there, like you could say, okay, if we have a customer and we barely know anything about them, most of the stuff is missing, let's delete that instance. In other cases, however, let's say that you're doing anomaly detection, maybe the fact that you don't know a lot about this person makes them interesting to begin with. So be a bit careful before you just like go for this nuclear option. Same for features. If 90% is missing in a feature, but for 10% you do have information, maybe that's a very interesting feature, right? So be a bit careful. Better is to replace the missing value instead, right? You impute the value with something else. And there the safest choice is kind of to pretend to the model, this is basically an average Joe, right? So don't pay too much attention to the value of this feature. They're basically simply the average. So meaning that for a continuous feature, you impute with the mean or with the median, which is more robust, right? If you have outliers present and you didn't remove those first. And for categoricals, you impute with the mode, which is the most occurring value or level of that categorical. And that's basically just a way, you're basically hiding, right? Because you do need to give the model something, but if your distribution of income is something like this, right? You will not impute with the most extreme value, right? You are not going to make everybody for which we do not know the income, we're not going to make all of these guys a millionaire, right? So just taking the average there is like the safe hiding choice. We'll see this idea of average and mode to represent average Joes popping up again when we talk about explanatory techniques. So you will see that there again. Now, you might say, well, wasn't the fact that it was missing in the first place then, don't we hide that, and wasn't that informative as well? So indeed, you can combine this with also trying to keep that information around as well. And typically what that means is that you do not just have an income column in which you imputed some values, but you also have an income was missing column where you have zeros and ones to basically indicate to the model, hey, be careful, we simply put the average in there. But you do need to know about the fact that actually originally that information was missing. And if this is correlated in some way to the target, well, maybe you can do something with that, right? So you add in a separate indicator feature to say that the value was missing or not. When you have a categorical, you don't really need to add in a separate feature. You can just add missing as a separate level in your categorical if you want to do that. So typically you use a combination of imputation and indication. Tools such as missing number in Python or VIM in R can make it easier to detect which of your features have the most missing values. So the common approach is to delete your rows with too many missing values, but be a bit careful, but to impute features using the median and the mode, and then add a separate column to indicate whether the feature was originally missing or not. You can make that more fancy. You could say, well, one thing that you could do is you could try to use a class level median, for instance, where you say, well, it doesn't really make a lot of sense that for temperature, if I need to impute it there, that I would use a single mean or median. Why would I also not incorporate the label? And I take the median of all the yes cases, and I take the median of all the no cases, right? And then depending on what you are, yes or no case, I impute with the no median or impute with the yes median to already make that a little bit more label informed, you could say. Yeah, you can do so. What's the issue if you would do that? What would be your problem? So you get the idea, right? Instead of imputing with one median value here, I basically look at, are you a yes case or a no case? And I take the median of all the yeses and the median of all the no's, and I impute with two separate values instead of one. Yeah? Exactly. Yeah. For new cases, you don't know the label, so what would you impute them with, right? This is also why it's so important to do your train test split first, because you will then see, ah, damn, I got into trouble. The solution then is not, let me just impute and the full data set together, because no, tomorrow you will still have new cases. That's exactly what the test set represents. Now you could try to overcome that. You could try ways to fix that, but it's never a good idea to incorporate the class label into pre-processing tricks such as these, because indeed for unseen cases you do not know the class label. What you could do instead, you do have the other features. So maybe a better idea is to then say, well, I cannot do it based on the yes median and the no median of play golf, but maybe I could utilize your other features to create like separate values there. And maybe that is a modeling task in itself. Maybe overall my question is, given that I have a missing value for temperature, but I do know your other features, what should I put in temperature here? I can build a predictive model for that as well, right? But then problem, but if you would use Outlook, humidity, and windy to build a model that predicts the temperature, what if windy is missing as well, right? Then you need to start somewhere, and you will have to build a chain, right? And you will say, well, first I will make a model that predicts feature 2 only using feature 1, and then I can have a model that using feature 1 and feature 2 together predicts me feature 4, and so on. And then the question is, what should the order of these operations be? What if feature 1 contains a missing value? Well, there we just use the median, right? And then you try to wrangle this about so that you have the best approach. Those are things that MIS4s do or auto-impute. Is it worthwhile in practice? I know that there are some people every year that love to pay an enormous amount of attention on missing value imputation. Typically, the simple approach is good enough. It's rare that in real-life cases, like spending hours and hours and hours on fancy missing value imputation will really give you that much better results. Not that it can't happen, it's just that it's rare, right? So there is a whole research area on this, right? But in real life, don't spend too much time, at least not in the beginning. First get like a baseline model up and running and see what that does. I will stop with today with this intermezzo, and like it was already mentioned, like the reason why you can't use your class labels is because you do not have them for unseen instances. Again, that's the reason why we split so quickly into a train and into a test set, right? So not just your model itself is part of the modeling pipeline, but also every pre-processing step that you do also becomes part of your deployed pipeline and will have to be able to be re-executed on new instances that appear, right? Meaning that every pre-processing step, if you would define them functionally, is defined over, you do some sort of pre-processing, and the input is a single instance, and they spit out a modified version of that instance, that's fine, right? You can take this function and apply it on new cases, old cases, train cases, test cases, tomorrow cases, yesterday cases. That's fine, right? If you have functions where you say, well, for this to work, I would basically write them, I want to apply them on an instance, but I need like a whole batch of data to give you the modified instance, then there is something strange going on. But that's effectively what you do when you do missing value imputation, right? There you say, well, I need a whole batch of instances because that's where my median value gets calculated from, right? Whenever you have something where you would say, my pre-processing step looks something like this, that basically means that you are creating something that has learned something. Why? Because this thing has a parameter. It has a beta, it has a weight, whatever you want to call it. Whenever you extract something from more than one instance, you're learning something, right? So this is basically something that is being trained as well. So here the operation is basically, well, first we trained this pre-processing step on my training data, batch train, and the output from this is a single weight, the median value of that feature. And then I have another thing that needs to reapply this thing on a new instance, given now I'm not relearning this all the time. I use my learned weights that I got from my training data. So in the case of a missing value imputation, that is why we use the median value for age, for instance, as we see it in the train data, not in all the data together, right? And I know the argument is, yeah, but wouldn't it be better that you can like update this feed or this value, this median value over time? Yeah, sure, retraining is always better. Same for your model, right? It would also be nice that you could just retrain your model every month. But that's not what we are testing. With this test set, we exactly want to figure out and be warned about the fact that if things have already changed too much between test and train, that we see that as an issue. It would be quite dramatic that even something like a median value of age would be something that would change so drastically between train and test. But who knows, right? Maybe your test comes from COVID and your train before COVID, right? At least you see the issue then. At least the goal of a test set is not to kind of take it as a game and let's try to figure out all the tricks that we can to get as high of a score on the test set as we can. The key goal of that test set is basically to warn you for potential volatility and data drift issues. That's the goal of a test set, right? So that's why making this split up front is so important, right? And no offense, but in that case, if you look at the API design of something like scikit-learn in Python, where also the pre-processing functions have a fit and a transform, just as their models have a fit and a predict, right? In R, sometimes the tutorials that you find, they will go, before we split the data, we will have to pre-process it. A very common like mistake, for instance, that you find there is, we have too many features, so we will do a PCA first. What do they do the PCA on? The full data set. No, you train the PCA on the training data and you reapply that transformation on your test cases. That's the proper way, right? Otherwise, you're cheating. So that's why you do this as quickly as you can and you put a test set in a vault, and it will also really be a test to then see, did all of the fancy pre-processing and feature engineering steps that I came up with, can I actually reapply all of these things on new cases? I gave you the example in the beginning. I said, let's make a clustering, and then I will use the distance between an instance and the cluster centroids as features, right? That would work here, but that does mean that you make your clustering solution on the train data, and then that you use that solution to kind of get your distance from the centroids for new cases, right? Which cluster do they belong to? That would already be more difficult. Cluster, well, yeah, I have my centroid, so yeah, closest centroid. But there might be things that you do, like if you would run unparameterized t-SNE, for instance, where you cannot reapply or reassign on new unseen instances. Right? So important to do that correctly. Good. That was the intermezzo. Keep that in mind. We will get back to that when we talk about evaluation. I will repeat that a couple of times, but that's quite important. Good. I think that's enough for this week. Next week we will continue with this. Keep an eye on Toledo for the groups, right? And for the recording, and see you next week.